So another type of network would that be of an electrical network. An electrical network is a type of network where analysis is commonly applied. An analysis of such a system uses two properties of electrical networks known as Kirchoff's law. So according to Kirchhoff, all the current flowing into a junction must flow out of it, and that the sum of the products, that is I times R, where I is current and R is the resistance, around a closed path is equal to the total voltage in the path. So in an electrical network, current is measured in amperes, or okay, we can write that one as A. Resistance is measured in ohms, okay, given in the symbol omega. And the product of current and resistance is measured in volts, which is denoted by capital V. Okay, we have here this symbol which represents a battery. The larger vertical bar here denotes where the current flows out of the terminal. The symbol, okay, we have here a zigzag, denotes resistance, and an arrow in the branch shows the direction of the current. Say, for example, we will have this electrical circuit. Determine the currents I sub 1, I sub 2, and I sub 3 for the electric network given below. So the first thing that we need to do is to come up with the conservation of the current. Okay, according to rule number 1, all the current that is flowing into a junction must flow out of it. So if we're going to take a look at this figure, we will have, say, junction 1. We can see that I1 and I2 enters junction 1 and leaves as, I1 and I3 enters junction 1 and leaves as I sub 2. So that we will have I1 plus I3 to be equivalent to I2. Now, the second condition, according to Kirchhoff, is that the sum of the products IR around a closed path is equal to the total voltage in the path. So we can see here that we will have this direction. We can have I1 times R1 plus I2 times R2 will be equivalent to the total voltage, which is 7. Okay, so we will have here I1 times R1, as well as plus here you will have your I2 times R sub 2 is equivalent to, so you have here that loop is equivalent to 7 volts. Now, as you can see, I1 times R1, and R1 is 3. So that means we will have your 3I1 as well as 2I2 is equivalent to 7. So again, let this be our equation 1. Let this be our equation 2. Now another loop will be at the second, okay, we will have here the second portion, or the lower portion. So again, we will have I3 times R3 plus I2 times R2 to be equivalent to 8 volts. Okay, so we will have here I3 times R3 and then plus I2 times R2 equivalent to 8 volts. And since R3 is 4, so we will have 4I3 as well as 2I2 is equivalent to 8. Let this be our equation 3. So we're ready to set up the system of linear equation. Let us summarize that one. So the system of equation will be I1 plus I3 is equivalent to I2. Or let's say that will be equivalent to 0. Okay, so since we will have a 3 unknowns, I1, I2, and I3, so we can express equation 1 as I1 plus I2 plus I3 equivalent to 0. And then for equation 2, we will have your 3I1 plus 2I2 is equivalent to 7. And we will have here 2I2 plus 4I3 equivalent to 8. Or the augmented matrix. So what will be the augmented matrix? The augmented matrix will be 1, 3, 1, 3, 0. And then we will have 1, and then 2, and then 2. And for I3, we have here 1, we have here 0, and then 4. And they're all equivalent to 0, 7, 8. Now, since we already have the augmented form of the matrix, we can simply apply our Gaussian elimination with back substitution, or proceed with the backward phase so that we will have the reduced row echelon form of the matrix via the Gauss-Jordan elimination method. So let's check our answer. So here we'll be able to see first applying the first law of Kirchhoff, wherein we find the conservation principle, and then doing the balance among the loops, and come up with the system of linear equation in 3 unknowns, transforming that one into the augmented matrix, as well as the reduced row echelon form. Obviously, this tells us that we will have a unique solution. That is I sub 3 is equivalent to 1, I sub 2 equivalent to 2, and I sub 1 equivalent to 1. So the system is consistent, independent. Okay? So we see how we can model real-life problems, which are actually systems of linear equation, and such as in polynomial curve fitting, and then network analysis. With all these problems, we already at least know that we can solve them using the principles of linear algebra.